So this is task 4.6, the warm-up. It's on page 29. So in the task of George W. Ferris's day off, you found Carlos's height at different positions on the Ferris wheel using right triangles as illustrated in the diagram. Recall from the following facts from our previous task. This Ferris wheel radius 25 feet, center 30 feet off the ground. Carlos has been carefully timing the rotation of the wheel and has observed the following additional facts. The Ferris wheel makes one complete rotation counterclockwise every 20 seconds. So question 1 asks, use this new information, how many degrees does the Ferris wheel rotate per second? Keep in mind that a full circle is 360 degrees, and if it's going a full circle or 360 degrees in 20 seconds, if you divide 360 by 20, you get 18. So that means for this Ferris wheel, it is rotating 18 degrees per second. So that's called the angular speed. Question 2, how high will Carlos be 2 seconds after passing position A on the diagram? Well, notice in the diagram they drew a triangle. It's a right triangle. So after 2 seconds, he's rotated 36 degrees counterclockwise. So he's really 30 feet off the ground, plus some additional amount because he is rotated past the axle or the middle of that Ferris wheel, and that value can be calculated by using some right triangle sine math and adding 25 times the sine of 36 degrees. So keep in mind in that diagram, if you were to figure out the sine of 36 degrees, it's going to give you that additional height, this little piece right here, divided by the hypotenuse, with opposite over hypotenuse. So that's why that h value is 25 times the sine of 36. And if you calculate that, that is going to be the value. So it's going to be 30 plus some additional amount, and the additional amount is 25 times the sine of 36 degrees. And if you grab a calculator and figure out 25 times the sine of 36 degrees, that will be that amount, and we'll write that down in a sec. So 25 sine 36 degrees, we'll go to the nearest tenth, is around 14.7. So if you add that to 30, he's going to be at 44.7 feet off the ground after he rotates 2 seconds counterclockwise. Okay, the next question for number 3 says, calculate the height of the rider at each of the following times, where t represents the number of seconds since the rider passed position A. Keep track of any patterns you notice and the ways you calculate the height of the rider. As you calculate each height, record the time and height on the diagram as the coordinates. Okay, so let's do a couple of these. We just did 2 seconds, and 2 seconds was 30 plus 25 times the sine of 36 degrees, and the height of the rider was, I believe, 44.7. Okay, let's go to 3 seconds. So at 3 seconds, if we go back to the diagram, 3 seconds the rider is going to be going 18 degrees per second. So 3 seconds is going to be a triangle you could draw up here. 3 times 18 is 54, so imagine at 3 seconds the rider is someplace here, and if you drew a triangle here, you would know that angle of rotation, because it would be 3 times 18 degrees per second, or 54 degrees. So you'd end up with that same kind of triangle where you'd find the sine of 54 degrees, and it would be this new value h, which is how high off the ground, over the same radius, which is 25. Except the only thing that changed was the angle. So instead of using 36 degrees for the angle, we're going to use 54. So at 3 seconds, that's still going to be 30, but it's going to be 25 times the sine of 54 degrees, and that's going to be the new height. So that's going to be 50, so 25 sine of 54 degrees is around 20.2, so plus 30 is going to be 50.2. So that's how high the rider is. If we go one more time, let's go to 4 seconds. So we take 30 and it's going to be 25 times the sine, but that angle of rotation is changing again. If it's 18 degrees per second times 4, 18 times 4 is 72, so it's going to be this calculation. And if you calculate 25 times the sine of 72, so do 25 times the sine of 72, that's around 23.8. So 23.8 plus 30 is going to be 53.8. And that's going to be how high the rider is. Question 4 says, examine your calculations for the height of the rider during the first 5 seconds. During this time, you're just rotating in that first quadrant, 0 to 90 degrees. Can you write a formula for the height of that rider? So let's go back and put one of those values into, they asked you to put the diagram as a time and height. Let's go to the 4-second one and put the time and the height. So it was 4 seconds and it was 53.8. So here's in the diagram, 4 seconds is going to be someplace over here. Let's say 4 seconds. If it was 20 seconds all the way around, so 10 seconds would be halfway around, which would be from A through F. So then 5 seconds would be up here. So 4 seconds might be someplace up here. So there would be this 4 seconds of rotation. And then the height for 4 seconds was 53.8. So this is going to be 53.8 feet. So those are all just points on that Ferris wheel. 1 point representing time, the x value in a sense, and then the other value, the y value, representing the height. So notice there's definitely a pattern to this. How are we finding the height of the rider as the rider goes around this Ferris wheel? It is 30 plus 25 times the sine, and then based on when the rider is rotating around, it was 18 degrees per second times whatever that time was. So that can be an equation you can use to find the height of the rider for this particular Ferris wheel. On page 31, they wanted to keep on going for other times as opposed to just the ones in the first quadrant. We're just going to do 3. We're going to do 12 seconds, 23 seconds, and 38 seconds. So at 12 seconds, the rider is going to be 30 feet off the ground plus 25 times the sine of 12 seconds times 18 degrees per second. And that'll give us a value. For 23 seconds, the rider is going to be 30 feet off the ground plus the rider rotates around 25 times the sine of 23 times 18 degrees per second. And at 38, same idea. It's going to be 30 feet off the ground plus 25 and this rotation amount, which is going to be 38 times 18. So I'll go through and calculate those. And notice at 12 seconds the rider is going to be 15.3 feet off the ground. At 23 seconds, which is more than a full circle, because a full circle was 20 seconds, the rider is back 3 seconds higher again, so or after a full circle, so it's 50.2 feet. And after 38 seconds, the rider has gone around almost 2 full circles, and the rider is only 15.3 feet off the ground. So what's happening math-wise is that sine is referencing the y-coordinate as you go around this Ferris wheel, and the axle represents the midpoint. So sometimes the sine gives you a positive value, sometimes it gives you a negative value, so the formula is keeping track in a sense of, are you adding or subtracting to that 30 value, which is the axle or the midpoint of that Ferris wheel, to give you the height off the ground. Question 6 says, how do you find the height of the rider for any other quadrants? Well, sine is an intelligent function, so if we call this function h of t is going to be 30 plus 25 times the sine of 18t. And these examples are just illustrating that this formula from previously is not just accurate in the first quadrant, it is accurate in any quadrant, because sine will add or subtract its calculation to the 30 value to give you the correct height above the ground. All right, on page 32, the task of 4.6, they're talking about a little more Ferris wheel. So in the previous task, you found the height of the rider as time passes, or we call our Ferris wheel 25-foot radius, 30 feet off the ground is the center or the axle of the Ferris wheel, and it makes one rotation every 20 seconds. They want us to go through and graph this Ferris wheel on this grid. So keep in mind it's going around at 20 seconds, and we're still starting at that farthest right position on the Ferris wheel, so the furthest right chair, and where that's going to be our time 0. So on this graph at time 0 you are 30 feet off the ground, so you can make a point at 0 for time and your height is 30. And it's helpful to think, okay, 20 seconds later I'm back to that same point. So in 20 seconds I am also 30 feet off the ground, so I'm back here again. And because the rotation is 20 seconds, that means after 10 seconds, I'm the same height off the ground. I'm just halfway around. So in 10 seconds, I'm going to be right here. And then because our Ferris wheel has a radius of 25, if I go only a quarter turn, I'll be at the top of that Ferris wheel in 5 seconds. So 5 seconds is in between 4 and 6. And the axle was 30 feet off the ground, the radius 25. So that adds up to 55 total. So at 5 seconds, I am at 55 feet off the ground, which is right about there. And then the closest I get to the ground is 5 feet above the ground because I'm 30 feet up from the axle, but the radius of that wheel is 25. And that happens when I'm 3/4 of the way around, which is 15 seconds. So 15 seconds is between 14 and 16, and I'm 5 feet off the ground. So here's 4, here's 6, so 5 is right there. So if you imagine the Ferris wheel is a nice smooth ride, connecting those points, this is the graph of the height above the ground of that Ferris wheel. So that's one rotation of the Ferris wheel. Okay, and we could do that one more time if we wanted, go 20 seconds in the future. So go to 40 seconds, and we are going to be back at the axle height of 30. Go 30 seconds, we're back at that axle height. At 25 seconds, we are at the highest point again. So at 25, we're way up here at 55, right around there. And then at 35 seconds, we are close to the ground. We're 5 feet off the ground, so that's going to be right about here. And that's another graph of, as time passes, how high I am above the ground. Okay, so that's showing 2 rotations of the Ferris wheel. Question 2 says to write the equation of the graph you sketched in question 1. No surprise, this is the equation. So it's h of t equals 30. We started at 30, and as we rotate around, it's 25 times the sine of 18t.